back to my original introduction of VSEPR, what I had said was that there are two things that can take up space around a central atom. Those are atoms and non-bonding electron pairs. So what I want to do now is show you an example of some of those that involve non-bonding electron pairs. Now going back to the one that has three objects around it, boron trifluoride, what we had said was, this is the one where we've got B with three F's around it. If these F's want to be as far apart from each other as possible, then they're going to have to be in an arrangement that's going to be a triangular type arrangement, all in the same plane. You can see that they're all in the same plane, with 120 degrees in between each of them. Now if we throw in a non-bonding electron pair instead of an atom, and an example of that would be sulfur dioxide, or SO2. Let me show you what the Lewis structure for that looks like, and that's what we're seeing here. We've got two atoms and we've got this non-bonding electron pair, and here I've shown you the non-bonding electron pair in a bubble to exemplify or to make sure you understand that this indeed does take up space, just as much as these atoms end up taking up space. So what we're seeing here is something that has the same overall geometry as BF3. So this one here and BF3 both have identical overall geometries. The lone pair ends up taking up just as much space as the fluorine does. So the overall shape of this, if we include the lone pair, is going to be called trigonal. However, if we decide we're going to not show the lone pair, this is what we're going to end up with. And the shape of this, not surprisingly, is called bent. The other way of naming this is called angular. Now it's not like we've removed the lone pair, it's just that I'm not showing it in the diagram. So what I want you to see here is that there's two possible ways that we can talk about shape when lone pairs are involved. This way we can talk about the overall shape when we're actually including the lone pair in the diagram, and we're including it in the overall shape of the actual structure. So this would be SO2 and the overall shape would be trigonal. When we remove the lone pair, because remember the lone pairs are invisible, we're not going to be able to see them. The only thing we're actually going to see are atoms. Then what we're looking at is just the shape of the atoms, and we call that bent. So there's two things that we'll talk about: overall shape and shape of the atoms. Alright, let me show you another example. We've got methane here. Methane has four atoms around it, and those four atoms are arranged in a tetrahedral type arrangement around the central atom. And as I had said earlier, this would be in the plane if I drew it this way, and this would be sticking into the plane of the screen, this would be sticking out of the plane of the screen, and the bond angles are all 109.5 degrees throughout methane. So this would be an overall tetrahedral shape. Let's take a look at something like ammonia. Now ammonia is NH3 and it's got one lone pair. There are three atoms and one lone pair, so there are four objects in total around the nitrogen atom. This is still an overall tetrahedral arrangement, just like methane was. Let me arrange the methane in the same way, and you can see that the overall shapes are identical. If we ignore the lone pair or just don't look at the lone pair, remember the lone pair is invisible because it's just electrons. The only thing we can actually see are atoms. This is what we get. And the shape here is called trigonal pyramidal. As you can see, it's the shape of a triangular based pyramid. The triangle would be these hydrogens here, and the tip of the pyramid would be the nitrogen. So this would be a shape of the atoms would be called trigonal pyramidal. The overall shape is called tetrahedral. That's the one where we're actually showing the lone pair. Right, let's take a look at water. And water, as you can see, has the same shape, or same overall shape at least, as ammonia and methane has. And you can see them all there. We've got four objects around the water. We've got two atoms and then two lone pairs. And again, if we take off the lone pairs, what we're left with is a structure that is indeed bent or angular, just as it was for SO2. And you can see that we're only going to see the hydrogen, the oxygen, and the hydrogen. The lone pairs are still here, we're just not showing them. So the shape of atoms here would be called bent or angular. Alright, so just summarizing, and I'll do this for methane. We can talk about two things. We can talk about overall shape, which includes the shape of, which includes the atoms and all non-bonding electron pairs. Like in ammonia here, this would be a tetrahedral shape because it has the same shape as methane, and the electron pair and the atoms both take up space. If we ignore the electron pair, well, we just don't show the electron pair, then what we're left with is a shape of atoms, and that shape of atoms will only show the shape of the atoms and ignore the electron pair here, and this shape here, for example, would be trigonal pyramidal.